In December 2015, SpaceX achieved a historic milestone by successfully landing an orbital Falcon 9 rocket booster back on Earth, marking the first instance in the history of human spaceflight. Over the subsequent 8 years, SpaceX has maintained its unique status as the sole provider capable of accomplishing this remarkable feat. Interestingly, no other rocket provider has attempted such a landing. This raises the question: how did SpaceX, seemingly out of nowhere, surpass companies with decades of experience in rocket launches? While some might attribute it to Elon Musk's unparalleled technological brilliance, we believe there's a more intriguing and gratifying explanation. Welcome to Spaceverse, your go-to destination for an interstellar journey through the wonders of the cosmos. Join us as we unravel the mysteries of the universe, explore the latest breakthroughs in the aerospace industry, and venture into the realms of interstellar exploration. Let's now delve into it. The pivotal factor that distinguishes SpaceX within the aerospace industry is its groundbreaking use of reusable rockets. SpaceX has redefined this technology in a way that was previously considered beyond imagination. However, it's essential to acknowledge that the concept of retaining massive rocket boosters instead of discarding them into the ocean may not be an entirely novel idea. After all, someone along the way likely contemplated the notion. Additionally, the space shuttle was already designed to be reusable, and even Blue Origin can land its rocket boosters similarly to a Falcon 9. Despite these precedents, some leaders in the aerospace industry argue that reusable rockets aren't inherently more economical or sustainable than traditional methods. They may dismiss the act of landing a booster as more of a showy maneuver than a genuine innovation. So, what truly sets SpaceX apart? To uncover the answer, we must revisit the origins of this revolutionary approach. The initial rocket boosters responsible for launching payloads into outer space were essentially repurposed intercontinental ballistic missiles. The Titan II, utilized as the launch booster for NASA's Project Gemini, had an original purpose of delivering a 9-megaton nuclear warhead halfway around the world. However, given their military origin, these boosters had inherent limitations in terms of reusability. Notably, the Titan II, designed for Project Gemini, had a specific function and could only be realistically expected to fulfill certain tasks. When the Apollo missions to the Moon were on the horizon, NASA opted to design its first custom orbital rocket, the Saturn V. This colossal vehicle, even today, surpasses nearly every rocket ever manufactured. Surprisingly, despite its size, only the relatively small crew capsule at the pinnacle returned to Earth. Their remaining components were either discarded in the ocean, left adrift in space, or abandoned on the Moon's surface. While this may seem like a squandering of funds and resources, it was, in fact, NASA's preferred approach at the time. The decision to make the Saturn V entirely disposable was economically sound given its limited intended usage of around a dozen missions. It was calculated that constructing 12 disposable rockets would be more cost-effective than developing a single reusable rocket. Furthermore, NASA's engineers were forward-thinking even before the first moon landing. Prior to the lunar missions, NASA had been conceptualizing the space shuttle, a fully reusable rocket plane and booster system seen as the key to sustainable human spaceflight. Wernher von Braun, NASA's chief architect of the Saturn V, had formulated his vision for the ferry rocket in the mid-1950s. Despite being recognized as the father of space travel in America, von Braun's background as a former Nazi rocket scientist only came to light after his death, leading to retrospective criticism. Regardless, the ferry rocket was envisioned as the vehicle that would bring human spaceflight into mainstream accessibility. The envisioned 3-stage rocket would boast full reusability, with the first 2 booster cores descending gently using parachutes and the 3rd stage orbiter gliding back to Earth for a runway landing. Exploring the ferry rocket concept alone could be a compelling topic for a dedicated video. Let us know your thoughts in the comments below. Interestingly, this concept bears similarities to what the space shuttle eventually became, although with fundamental design differences. While commonly referred to as a reusable spaceplane, the more accurate term is often considered to be refurbishable. Now, what's the distinction? At an airport, you can witness a plane landing, unloading passengers and cargo, undergoing a swift cleaning, restocking, and refueling before boarding a new set of passengers and taking off all within an hour or even less. In this context, a commercial airplane is safely labeled as reusable. Contrastingly, if that same airplane had to be entirely disassembled, inspected, serviced, and reassembled after each flight, it no longer fits the definition of reusable. Moreover, it sounds like an unsustainable way to operate a commercial airline. This is the challenge NASA confronted with the Space Shuttle. While it technically fell under the category of reusable, aligning with the initial criteria set by the U.S. Congress when the shuttle was funded in 1972. The actual process of returning a space shuttle and its twin booster engines to the launch pad after a single flight required approximately 650,000 hours of combined labor for transportation and refurbishment. Notably, this labor was concurrent, not sequential. Otherwise, it would take 74 years to refurbish one space shuttle. The crucial factor with the reusable rockets lies in their economic viability, hinging on the frequency of launches to outweigh the costs associated with developing and employing such technology. As discussed earlier, this is the reasoning behind NASA's decision to opt for 12 disposable rockets rather than investing in a single reusable system. Determining the economic feasibility of a reusable rocket raises the question of how many launches are needed to make it a sensible choice. Unfortunately, NASA didn't have the opportunity to ascertain this threshold. The Space Shuttle, intended to be reusable, faced unforeseen challenges. The refurbishment process turned out to be more extensive than anticipated, and the shuttle never achieved the frequency of launches initially envisioned by NASA. In the end, it would have been as cost-effective or possibly even cheaper for NASA to discard each space shuttle after a single flight and build a new one from scratch. This experience with the Space Shuttle serves as a deterrent for commercial rocket companies considering the development of their own reusable vehicles. The Space Shuttle, being the most expensive rocket ever developed, also proved to be the most dangerous and arguably the least successful in fulfilling its original design concept. Observing this, commercial companies may have been discouraged, reasoning that if NASA, with all its resources, couldn't achieve sustained success with reusable technology, then the odds were against anyone else succeeding in the same endeavor. Enter SpaceX, breaking the mold by setting out to succeed where others had faltered. To be fair, SpaceX approached the challenge from a markedly different perspective than NASA did with the Space Shuttle. The Falcon 9, in many ways, reflects a more logical and efficient logistics strategy. From the outset of their development, SpaceX, starting with the Falcon 1 rocket, envisioned the recovery and reuse of both the first stage booster and the upper stage vehicle. Their plan involved executing a propulsive return to the launch site and a landing maneuver. Although SpaceX abandoned the idea of recovering the second stage relatively early in their development, this concession was reasonable. In traditional rockets, the upper stage is a relatively straightforward vehicle, comprising just one engine, a couple of small fuel tanks, and a platform to hold the payload until deployment. However, the recovery of the first stage booster presented a significantly more valuable proposition. The key was to make the booster fully reusable, not merely refurbishable, and to operate it frequently enough to justify the additional effort and investment. Certainly, SpaceX embraced one of the most technically challenging recovery methods available: propulsive landing. This approach marked uncharted territory compared to Wernher von Braun's earlier ferry rocket concept, which relied on boosters landing in the ocean water under giant parachutes, with engine firing assisting in the descent. NASA's success with recovering the Space Shuttle's twin booster engines involved parachuting them back down after stage separation. However, when it came to the Falcon booster of SpaceX, using parachutes proved to be infeasible due to the constraints of physics. The key differences lie in the nature of the boosters and the rocket design. The Space Shuttle boosters were relatively small and light, being solid rocket boosters that essentially became empty metal tubes after burning up all the propellant. Additionally, they separated at a relatively low altitude and, consequently, a lower velocity of around 43,800 km per hour. Their primary role was to assist the shuttle in overcoming the initial challenges of getting off the ground and through the thickest part of the atmosphere. After this phase, the shuttle still had three powerful hydrogen-burning RS-25 engines to achieve orbital velocity. In contrast, a single-core two-stage rocket like the Falcon 9 relies on one booster to impart a substantial amount of velocity to the upper stage. This is crucial for the final vacuum engine to continue accelerating the payload into orbit. The design and function of the Falcon 9 demand a different and more complex recovery method, leading SpaceX to pursue the innovative approach of propulsive landing. The Falcon booster's higher altitude and faster speed exceeding 8,000 kilometers per hour at stage separation, pose a challenge for parachute-assisted landing due to the immense kinetic energy involved. The kinetic energy formula, 1/2 mass times velocity squared, results in too much energy for parachutes to handle after the release of an orbital payload. Wernher von Braun's concept involved a hybrid approach, combining engine deceleration with parachute-assisted landing. However, Elon Musk's philosophy, encapsulated in the mantra "the best part is no part," emphasizes efficiency and simplicity. In Musk's vision, since the Falcon 9 already has engines, there's no need to complicate matters by adding parachutes for velocity reduction, when the engines can perform the same function. Moreover, the Falcon 9 engines serve a dual purpose, acting as a free heat shield to protect the booster during re-entry into the atmosphere. In a drone ship landing scenario, after clearing the atmosphere and technically entering space for about a minute, the booster begins its descent. As it falls back, the booster flips around and initiates a re-entry burn using its engines. This burn reduces velocity and creates a protective force field beneath the rocket to shield it from the extreme heat of re-entry. The spectacular cloud of smoke and fire, resembling a jellyfish, forms underneath the descending rocket. The booster continues its descent, guided by aerodynamic grid fins that help control its trajectory in the atmosphere. In the final moments, the engines reignite to ensure the booster's velocity reaches zero precisely when the landing legs touch down on the floating platform. SpaceX has successfully executed this procedure over 100 times, making it seem routine. However, it's crucial to note that achieving this level of reliability took SpaceX multiple trial and error iterations and upgrade cycles. The Falcon 9 only reached its true status as a genuinely reusable rocket with the introduction of its final form, the Block 5, in 2018. Typically, rockets undergo minimal active development once they commence operation. The design established during the initial successful launch is often maintained throughout the product's lifecycle. This approach stems from the inherent unpredictability and danger associated with rockets. Introducing design changes poses the risk of unknown variables that could lead to failures, a scenario that is generally avoided. However, SpaceX, guided by Elon Musk's philosophy of embracing failure as a marker of innovation, diverges from this conventional mindset. The first version of the Falcon 9, known as Falcon 9 version 1, was notably smaller, measuring about 46 meters in total length and less powerful, generating just 1.1 million pounds of thrust. Even though SpaceX intended to make the Falcon 9 a reusable booster from the outset, this initial version lacked the necessary grid fins and landing legs for reusability. The decision was to prioritize successful launches before delving into the complexities of returning the booster. This Falcon 9 completed 5 missions, including one to deliver a cargo Dragon capsule to the International Space Station, or ISS. Following Falcon 9 version 1, the next iteration was Falcon 9 version 1.1, which underwent significant changes, growing to over 68 meters in length. This version introduced the Merlin 1D engine and the circular octa-web engine layout, resulting in an increased total thrust of 1.3 million pounds. The enhanced size and power made Falcon 9 version 1.1 the first in the series capable of a controlled return to Earth, with sufficient fuel to execute re-entry and landing burns. SpaceX began experimenting with controlled landings through small-scale tests, attempting soft landings over the open ocean. The introduction of landing legs occurred during the CRS-3 mission in April 2014, while the addition of grid fins for more precise control during freefall took place during the CRS-5 mission in January 2015. This progress led SpaceX to attempt their first ever drone ship landing on the CRS-5 flight, coming surprisingly close despite initial skepticism. None of the version 1.1 rockets successfully landed. In June 2015, a mid-air failure during a Falcon 9 launch prompted SpaceX to halt operations temporarily. This setback led to another revision in the booster design, resulting in Falcon 9 version 1.2, also known as Falcon 9 Full Thrust. Slightly longer at 70 meters, it featured a significant increase in power to 1.7 million pounds of thrust. The boost in power primarily came from SpaceX's innovation of cooling their liquid oxygen and rocket fuel to lower temperatures, thereby increasing energy density. This commitment to learning from failure materialized in the first successful landing of an orbital rocket booster in the history of spaceflight, with the booster touching down on a SpaceX landing pad at Cape Canaveral during the inaugural launch of Falcon 9 Full Thrust. The Falcon 9 full thrust underwent several small tweaks and variations over the years as SpaceX worked towards finalizing the rocket into its ultimate form. The motivation behind these adjustments was the goal of obtaining Falcon 9 crew rating from NASA. While experimenting with variables is acceptable when only money and equipment are at stake. Once a rocket is designated safe for carrying human beings, further modifications must cease. This evolution culminated in the Falcon 9 Block 5. The Falcon 9 Block 5 retains the exact size of the previous version and only experiences a slight increase in power, reaching 1.8 million pounds of total thrust. Notably, the most visible distinction between these variants is the black paint applied in the middle and on the landing legs. The primary enhancements focus on elevating the overall reusability of the rocket booster. As discussed earlier, there's a distinction between reusable and refurbishable. While the Falcon 9 full thrust was refurbishable in certain situations, SpaceX mainly recovered those boosters and did not frequently reuse them. The inaugural SpaceX launch utilizing a refurbished Falcon 9 occurred in March 2017, utilizing a booster that had been recovered over a year prior. In the Block 5 version of the Falcon 9, SpaceX implemented several crucial changes. The turbopumps inside their Merlin engines were upgraded after the discovery that these units developed very small micro-cracks following launch and recovery. Simultaneously, the grid fins on the rocket side underwent reinforcement, transitioning from aluminum to titanium metal. Despite the high cost associated with forging these fins, they became the largest single pieces of titanium ever made. This upgrade significantly enhanced their resistance to the heat of re-entry and provided greater control over the rocket's angle of attack as it coasted through the air. To further enhance the Falcon 9's thermal protection, the entire body received a thermal protective coating, reducing heat absorption across the entire rocket. Additionally, a new reusable and replaceable liquid-cooled heat shield was added to the base of the rocket, offering enhanced protection for the engines and plumbing system. The landing legs on the Block 5 were upgraded to allow both extension and retraction, a significant improvement over the previous legs that couldn't fold back up after recovery and had to be unbolted and removed. SpaceX also addressed concerns related to composite overwrapped pressure vessels, or COPVs, on the Block 5. These ultra-high pressure tanks, wrapped in carbon fiber, store helium gas to maintain pressure inside fuel tanks as they empty. A COPV failure had been linked to both of the previous Falcon 9 explosions, one in the air and one on the launch pad. As of now, it has been 5 years since SpaceX implemented reusability upgrades to the Falcon 9. The question arises, did they succeed in creating a truly reusable rocket? This summer, on July 10th, SpaceX achieved a milestone by successfully launching and landing Falcon 9 booster B1058 for the 16th time. Notably, this booster was the same one that transported astronauts Doug Hurley and Bob Behnken to the International Space Station in May 2020, marking the first crewed flight on a SpaceX rocket. In just over 3 years, B1058 completed 16 flights. Initially, SpaceX anticipated that the Falcon 9 Block 5 would be capable of up to 10 launches and landings. However, this projection increased to 15 launches in 2022, and currently, SpaceX has certified B1058 for up to 20 launches, based on extended life vibration testing conducted by SpaceX engineers. There is confidence that the Block 5 could withstand as many as 60 launches and landings. For context, the Space Shuttle Discovery, the most prolific shuttle in the fleet, completed 39 missions. On average, there were only between 5 and 8 Space Shuttle launches annually, with a total of 135 missions spread across 30 years and 5 vehicles. Despite limited precedent, the available data suggests that the Falcon 9 is an extremely reusable rocket booster and has proven to be highly successful in this regard. So, now, we await the next leap forward. Can the Starship elevate reusable rockets to the next level? Join us back here every week for more updates on everything related to the aerospace industry and interstellar exploration. If you enjoyed the video, don't forget to give it a thumbs up. Your support truly matters. Subscribe to the Spaceverse for more videos similar to this.